Okay, in this video we're going to look at another application for eigenvectors and values, and that's to the solving homogeneous systems of first-order linear differential equations, something near and dear to the heart of most engineering students. So remember that we have a first-order system of linear differential equations would look something like this: y1, y2, y sub n. We're going to do y1 prime, and you're going to have scalars for y sub 2, y sub 1, y sub 2 through y sub n. Okay, so we can write this in a vector form, right? So y bar would just be y1 through y sub n. Those are the functions. And y1 y bar prime would just contain the y1 prime, y2 prime, y sub n prime. So we can write that as a matrix equation: y bar prime equals ay, where a is just the coefficient pieces from that system of linear differential equations. All right, so now how do we solve this, right? So we've got y bar prime equals ay bar. How are we going to solve this thing? Well, remember kind of how you did this for ordinary linear differential equations when you took dE. If the matrix A is just a single entry, then I have dy dt equals ay. Separate the variables, integrate, exponentiate for simplification, and we get y equals c1 e to the at. Right. And if you remember from differential equations, you might have two of those, right? a1 and a2, roots of the, however, if you have a second order differential equation, you'd have two roots, third order 3, and so on. Okay, so now y bar prime equals ay should have something similar. And I'm going to go ahead and put in the lambdas because you know it's going to involve eigenvectors and eigenvalues. So we could say, hey, a solution is going to be y bar is equal to e to the lambda t x bar. Remember here, I'm looking for functions of t, so here it is. Y sub 1 will be e to the lambda t, and x bar is just constants. Okay? It's just constants. Since it's just constants, then the derivative, y bar prime, is what? Pull down the lambda, because derivative of e to the lambda t is lambda e to the lambda t, and the x bar is just constants. They stay in place. So remember that x bar, that's just scalar constants. All right. So now what I'm going to do is I'm going to take those two things and substitute them back in here. So y bar prime is lambda e to the lambda t x bar, and ay bar is a times e to the lambda t x bar. So now what am I going to do? Hey, guess what? I can just divide those out, right? And that gives me lambda x bar equals a x bar. Subtract a x bar, or lambda x bar, from the right-hand side and the left-hand side, and you get a minus lambda I, right? So since this is lambda times x bar, when you want to pull it in with the a, you just do lambda times I. That's the same thing as lambda times x. Equals the 0 vector. Voila, lambda and x bar are eigenpairs. So in general, and I got the bottom of the screen here, if you have y bar prime equals ay, then one of those solutions, right, y bar prime, or y bar I 1 of t is e to lambda it x bar sub I. So where lambda sub I is an eigenvalue and x bar sub I is an eigenvector associated with the eigenvalue. Now recall from differential equations that linear combinations of solutions are also solutions. And what keeps us from infinitely growing solutions is that those have to be linearly independent y sub i's. Then linear combinations of those are new solutions. So the general solution then is going to be y bar equals c1 y1. I'm just going to do two cases here, okay? and that's C1 e to the lambda 1t x bar sub 1 plus C2 e to the lambda 2t x bar sub 2. Okay, and this is your eigenvalue and eigenvector pairs there. So let's look at an example. So find a general solution to the system of first order linear differential equations. So I've got y1 prime equals 2y1 plus 4y2, and y2 prime is minus y1 minus 3y2. So the first thing I'm going to do is write that, get some red, write that as a matrix equation. And looks like I forgot my prime there, right? Okay, so once I do that, I recognize immediately what? Need to find the eigenvalues and the eigenvectors for that matrix A. And hopefully you're okay with me not doing those out for you here, as we've done plenty of examples of finding eigenvectors and eigenvalues. So this has two eigenvalues, minus 2 and 1, and two eigenvectors. Right, so linearly independent eigenvectors, we're in good shape, no problems here. And voila, I write the solution. Y bar equals C1 e to the minus 2t minus 1, 1, C2 e to the t minus 4, 1. So that's pretty nice to solving those. Now, there's a lot of, I skipped over a bunch of work finding this. So the work is all finding the eigenvectors and the eigenvalues in this part of the problem. Right, now, that's kind of how we write the solution, just to make sure that you're fully aware of what I can run all of that together, right? So I can run the C1 e to the minus 2t in here, right? And I can run this one in here. I can then add them. This is a 2 by 1 matrix, and from that I get an equation. I get y1 and I get y2. So y1 is minus C1 e to the minus 2t plus minus 4C2 e to the t. Well, I've got those constants in there. It'd be nice to get rid of those. We need some initial conditions in order to find the exact solution, the general solution, using y1 of 0 is equal to 1 and y2 of 0 is equal to 1. So how am I going to do that, right? Well, notice that what? It means that y of 0 or y prime at y at 0 is 1, 1, okay? Because y naught and y1 naught and y2 naught are equal to 1. I can then go back and evaluate, and I'm going to go back up here and do this form here, I think. Yeah. So at t is, all of this at t is equal to 0 is what? E to the 0 is 1. So this just becomes C1 times the column and C2 times the column. So, right, so this is e to the minus 2 times 0, and this is e to the 0 equals 1 equals 1. Okay, and so here's the initial conditions. Here's what our equations are at that initial condition time t equals 0. They have to be equal to each other. Okay, and hey, look, I'm going to rearrange that. Hopefully you should be very excited. This is ax equals b, and we get to use linear algebra to solve this as well. I'm just going to solve for c bar by using the inverse of that matrix A there, and I'm going to get 5/3 minus 2/3 for c1 and c2, and I'm going to go ahead and write them in here. Now I'm not going to run them through again, but if you wanted to find y1 and y2, you certainly could, the same way I did before. Notice that, you can notice that if I use some, suppose I normalize this, so that would be minus 1 over square root of 2 and 1 over square root of 2. If I normalize the length of the eigenvector when I found it, the undetermined constant is going to absorb all of that. So you really, we tend to like them, use them with whole numbers or with integers here, but the undetermined constants or unknown constants in the differential equation will take care of whatever differences you use if you use a different eigenvalue vector than I used. All right.